Hey everyone, let me just check that, yeah, this has started. Sharing the screen. Okay, choosing the layout. Let's go. Another hard problem that I haven't solved before. So the problem, as you have seen, is minimum number of refueling stops. Okay. Let's see. What's this about? Car travels from a starting position to a destination which is at target miles east of the starting position. So car starts on the right and moves to the left. Oh no, to the right. Starts on the left. Yeah, I'm just mixed up east and west. Okay, there are gas stations along the way. The gas stations are represented as an array stations, where stations I is position and fuel. Okay, so we have stations, which is a list of integers. But each station has just two integers associated with it, so its position fuel is miles east and starting position and has fuel I liters of gas. The car starts with an infinite tank of gas which initially has start fuel liters. Okay, so I think we also have target, which is an integer, and start fuel, which is an integer. It uses 1 liter of gas per 1 mile that it drives. Okay, when the car reaches a gas station, it may stop and refuel, transferring all the gas from the station into the car. Return the minimum number of refueling stops, so we are returning an integer. If it cannot reach the destination, return -1. Note that the car reaches a gas station with 0 fuel left. The car can still refuel there. Okay. So tests and challenges. So before we go into tests, I just want to highlight that theoretically there is, if we have n stations, then of 2 to the power of n runtime for this algorithm, because for each station we can either choose to stop there or choose to not stop there. And then we can see the pattern that depending on what were the stations that we have stopped so far, this defines what we can do next and whether we can do something next. So we cannot just solve this problem linearly, at least it looks like it, because any new decision depends on all the previous decisions that we have made so far. So let's now speak about some tests. So let's say that there is, okay, so station. Let me actually write test like this. So let's say this is the whole distance that the car needs to go. So it essentially starts here. And on the other side here, we have a target. And then we need to figure out whether the car can reach it, what's the minimum number of stations that the car can need to stop at. So let's say it starts with 9, right? And then here, let's make it shorter. First, let's make it shorter. Example, okay, let me copy this. Now let's do that. So yeah, in situation like this, we need to make 0 stops, and we can just reach out our destination. Then let's say it starts not with 9, but starts with something like 3. And then it will be -1 because we cannot reach our destination. But then let's say that it starts with 3, and then we have a gas station here, for example. Okay, so we can travel 1, 2, 3 steps. So let's say it's somewhere here, and it gives us 5 more. And then we just need to make 1 stop here, and then we can go further, right? But now let's finally have a situation where we have several solutions. So let's say that here we have 1, then here we have 5. No, here we have 2, here we have 3, and here we have 1. So if it stops on this station, it can refuel and then stop at this station and refuel and get to the destination. But if it doesn't stop at the station, it will still have enough fuel to go to this station and then get to the destination. So in reality, here is better not to stop at this station and just go right to the end of it. And I think we don't even need this more complex example. So let's talk about the solution. I immediately start thinking about a dynamic programming solution, and I immediately start thinking about a pattern like dp of I will be how many stops to get to station I, how many minimal stops to get to station I, right? That's one of the ideas that I have, but how can I then figure out for the station I plus 1? Is it possible? So let's see. So for example, here for this station, we need to visit 0, right? So let me just write it like this. So here we need to visit 0. Maybe let me create another example that is a little bit more readable. So let's say we have 3 here, and then 1, 2, and then we have 1 here, and then stop. Okay, let's say we have 4 here, 1, 2, 3, 4, and let's say 1, 2, 3. Let's say we start with 4, and we can travel like this, right? So 3. So there are several opportunities, right? First is we start here, we go and stop at the first station, and then we can go we don't have enough fuel to go to the end, so we need to stop again here and then go to the last station. Or we can just go to this station with 3 fuel, and then we will go to the end. So the solution is 1. And then it's a little bit clearer how we can figure things out. So let me also say that if we know dp of I for next stations, configure min. Okay, so if getting to this station requires k steps, yeah, there is one important observation. If getting to I station requires k steps, and I see that there are some messages in the chat. Hey everyone, happy to see you here. Okay, so if getting to I station requires k steps, then getting to any j smaller than I station requires at least k steps. So it cannot be that we can get to this station in like one step, but to this station in only in 2 steps. So if we can get here in one step, we can here in one step, we can go to any of the previous, at least in the same amount of steps, in the same amount of stations visited. You see what I'm saying? So then, if we come to any station, we can figure out. So we got to this station. Let's say we got to this station with 1 step. How far can we go with this amount of steps, right? So basically, we start here, and then we iterate over stations, and then for this iteration, we see how far can we go using this view, right? So what's important here is that we kind of have like several dictionaries or something. What I'm thinking is, right, like we start at 0 and we start iterating. We go to the next station and its station is 4. So now we know that this station is at index, its position, like this is 0, so this is 1. So we get to station at position 0 with fuel 4. So now we know that we can get to up to position. So we start with, okay, so we know that we can, when we start, we know that we can get to position up to 4 with 0 steps. Then when we visit the first station and we see that there is some number here, like some number of fuel here. So at position 1, we have 4 fuel. So it tells us that we can get to position 5 at, we can get to position 5 at 1 step. Or, okay, it's 1 plus 1, 2, 3, 4. Yeah, so position 5, so 5th index. So we can get to, no, to 3rd index. Like if we have 4 fuel, we can get to 3rd index in 0 steps, to 5th index with 1 step. And then we continue. And then for each station, we need to find how many stations did it take for us to get here? Like, what's the minimum number of stations to get to this station? And how do we do that? We basically do a binary search here. And we will have like some distances where it takes, like, for example, us 3 steps to get, like if this position will be somewhere on this range, right? So if it's not somewhere in this range, if it's bigger than a position 5, so we basically cannot ever get to this because there was no previous station that could take us that far. And otherwise, we will try to figure out like what's the smallest amount of steps that gets us to this position. And then we need to modify this, right? So if it's k position to get to this station, then we know that now we can add this fuel from this station, and add K and modify like whatever happens in this list for future positions. So the problem is how many stations do we need to store? And I have discussed all of these things, but we will need to be much more precise in our definitions of what we need to do for each station. So I'm thinking what will be the algorithm, right? So let's maybe quickly hash it out in pseudocode. So we have like, let's say we have a sorted dictionary, right? And then it can be up to of n size. And in this sorted dictionary, we will be storing like number of steps, num stations, and farthest we can go with this number of stations. Then when we get to a new station, oh, it's vice versa, right? So num stations. So we will be ordering by this. This will basically be a position. So farthest we can go with this number of stations. And we can even drop items from the list. So can it be a double-ended queue? No, because we will need to remove things from the list possibly. But it might actually be something reasonable, like a double-ended queue. So let's say we arrive at position K. So for position K, we just start dropping things from our double-ended queue, from the left side of the double-ended queue, that stores things like farthest we can go, and then number of stations, right? So essentially it will be something like we can get to position 5 with 1 station, and then we can get to position 7 with 2 stations, and then we can get to position 12 with 3 stations. So this is the thing that we are storing, and we are updating this as we go. So once we get to position K, let's say we get to position 6, and position 6, and there is a station fuel equals, let's start with 4, right? So if we are at this position and fuel is at 4, so how we start dropping things from the left side of our double-ended queue. And we check that this number on the left is smaller or equal to our current position. So if it's smaller or equal to our current position, then it means that we can get basically in one stop to this position. So then, oh, but we cannot drop it. Yeah, we cannot drop it. We need to find, because maybe we are still at like position 6. Oh no, yeah, if we haven't updated this, so it means that like in one station, we have already got to this station to position 6, and we couldn't get to position 6 in one station. So we can feel free to drop it. So we are dropping the first item, and then we are left with that we can get up to 7 with just 2 stations. So that is the definite truth, that we have to use that. So now we know that we have gotten to this station and we have 4 fuel. So what does it mean for us? So it means that we can iterate over the next stations. And for example, here we are at position 6 and we have 4 fuel. So we can get to position up to 10 with just 4 fuel. So it would be, so position 10 with 3 stations, right? Because we got to this position with 2. We know that from this first line, first element in our double-ended queue. And this means that we can get to 10. So then we start checking where, like, which distances are now dominated. So this is one scenario, right? So here, this new possibility of getting to position 10 with 3 stations is not as good as getting to position 12 with 3 stations. So we are not doing any updates. But let's say that we are in the same situation and we need to get to position, and we have 10 fuel. So we again drop this first element from this list. So we now know that we can get to this current position with at least 2 steps. And then what we need to do is we now dominate with this solution, with getting to this station in 3 stops. We know that we can get, okay, after these 3 stops, we can now get to position 6 plus 10, so up to 16. So let's say that there is this, and then 15 and 4, and then 19 in 5, right? So what does it mean for us? It means that we have figured out a way to get in 3 stops farther than we could previously get in 4 stops. So does it mean that we can just drop those elements? So let's say we are dropping this, and not dropping, but we are like, we will store it just in case we will find that at 7th position there is another station with even more fuel. So we are basically saving this. But now this part is definitely dominated by this new solution. So it goes 16 in 3 stops. But if we can get to 16 in 3 stops, it should change also, like, what I'm trying to figure out. Do we just drop this, Or do we have in some kind of way to update this? I don't think that we need to update this. We can just drop this. Yes. So we just drop this. And then what's left is this last station. So this is how we update um, the list. So we go over, we select the, we leave the current element within the smallest amount of stations, and then we start dropping elements one by one from this list. And then we just insert those elements back to this double-ended queue from the left. So it will always be up to, like in total, it will be up to n elements that we will need to drop. But the thing is that we are just once, uh, we, we will never add the same station again to this double-ended queue. So we are adding at most n elements to this double-ended queue. And yes, sometimes we like remove it from the left and then add it back. But it doesn't change anything for us in terms of running time complexity, because it will be basically we are just dropping elements, and then we are getting putting at most 2 elements back on this double-ended queue. And I was saying double-ended queue throughout this time, but essentially it's not a double. We don't have to do a double-ended queue. We can just do a stack. So it will be a stack where we are just putting the further destinations down the line. And once we get to a destination, we will also need to check if this particular position that we are checking, if it's bigger than our target. So can position be bigger than our target? I don't think so. But then, yeah, once we have exhausted all our stations, we will just need to check for the target. We will have like a list of destinations and the number of stations ordered list. We will have to, again, just go through this with our target and figure out where the target should be. We can do it in O of n time, or we can just do a binary search to achieve that in logarithmic time, but it will not improve the running time complexity of this algorithm. Okay, so that was a tough solution. Doesn't involve dynamic programming at all, but it will take us of n runtime and of n space. So when I was saying that this looks like it cannot be solved in linear time, I was wrong. It looks like, at least. Okay, so let's now do the implementation. But before that, I will read the chat because there are quite a lot of messages there. Okay, what's up? Oh, any tips to clear the dynamic problem is easy. Just do a lot of dynamic programming problems, and feel free to also stream your suffering on YouTube. What's up, one? Which question are we doing? We are doing 871, minimum number of refueling stops. Yeah, sorry, I didn't answer before. Is full stack dev worth it in 2026 or just backend? Good question. I think the main constraint is always how much effort do you want to put into something. So if you want to put more effort into being a full stack developer, if it's something that's interesting for you, then you will just put more effort, learn more things, and be a better engineer, and be better. Because of that, you will be more valuable, you will earn more. If you just want to optimize for something, if you don't have a real interest, it will be harder, still achievable. Some people are just ambitious. They hate coding, they hate everything, but they like money, so they can still optimize for the specific career that benefits them. But in my experience, it's mostly the better the engineer I see, the more is this engineer enjoying what they were doing, what they were learning. So if you enjoy full stack more, then you should be doing full stack. If you just prefer backend, do backend. Just whatever you do, do it properly. And now back to my implementation. Okay, so stack will be this. And then actually it will be not just this, it will be that we can get to start fuel index with 0 stops. And then for station in stations, actually for, let's say, position, and then position min stops in stations. Okay, let's see. You're welcome. For position min stops in stations. So what do? We try to modify our stack. So it's kind of a monotonic stack problem, turns out. At least my approach is monotonic stack. So if yes, we will always have an element on the stack. So this is an invariant here. Because of that, I can always check if the last element on the stack, okay, not even if, while, so last element stack -1, this is the last element, and then the position will be 0 is smaller, or yes, it's smaller than or equal. Yes, smaller or equal. We need to remove the element from the stack. Then position. So while this is the case, okay, and I think here we can actually get to the situation where the stack will be empty and we will be popping elements here. So while stack and stack is smaller than position, will be that farthest distance and num stops will be stack pop. Farthest distance and number of stops. Okay, we are popping this from our stack, and we are doing this until we get to some position that is exactly like the next one is not smaller than the current one. So in this case, it will be, yeah, we'll have position 6. So we iterate over this list, and while this first number is smaller or equal to the current position, we are popping elements from the stack. Once we do that, we are done, and now we have farthest distant number of stops. So always we start this loop with something on the stack. So okay, actually, if stack -1 and 0 is bigger than position, we can just return -1. So here, if it's bigger, we can return -1. And now we know that when we get to this loop, it will never be bigger. So we will always get farthest distance and number of stops defined after we iterate through this loop. So now we will also know that we will drop all the elements that we need to drop. So now new farthest will be farthest distance. Oh, for position. Oh, no. For position and fuel stations. Mean stops we store in stack. Position and fuel are stored in stations. So new farthest is farthest distance plus fuel. And then we now have while new farthest while stack. So if we still have elements on the stack, and new farthest will be bigger or equal, just in case. In case we are seeing the element, for example, let's say we are getting exactly to 16, or not exactly, like exactly to 15, but previously we could get to 15 with 4 stops, and now we can get there with 3 stops. So we still want to pop the element that is close, that we can get to, and in the worst case we will just then put it back on with the same amount of stops. Okay, while stuck, and new farthest is bigger than stuck -1 and 0. While this is bigger, we do stack pop. So we are just removing all such elements. And then once we finally have done everything that we needed to do, then we do stack append, and we append 2 elements. The first element that we append will be the new farthest, right? So we can get here in the num stops num stops +1. This is the first thing that we are appending, and then the second thing that we are appending will be the previous position. So here we will still need to append 7 2, because we might still use that in the future, maybe on the next station or on the next position there is another station and it will still be relevant. So new farthest, and we need to put back farthest distance and num stops. Okay, so now we have iterated through all the stations, and if we found a station that we cannot reach, we just return -1 right away. But then now we have the target, and now we need to figure out whether we can reach our target. So while while stack and okay, while stack actually that will be simpler. While stack we do oh, I see the problem. We have iterated through the whole list, and we have already dropped element from the beginning of this list, because we are assuming that target will be somewhere farther away. But what if it's like even before that, we have already dropped this element after some iterations? What if it comes here, right? Like that we can get to position 5 with 1 stop. So what if our target is 4? We need to check that before we actually drop everything. So we need to figure out how do we figure out our target? So actually, let's do this first. I can do it in two ways. When I'm popping from this list, right? So if I'm popping it here, I can just see if my new station is past the target. I can also modify stations so that the target is not past them. Or finally, I can just do that when I'm adding a new station. So if my new farthest distance is finally smaller than is finally farther than the target, farther or equal to the target, then I can just remove the number of stops, new farthest. If new farthest is smaller or bigger or equal to the target, I can just remove new farthest. I can just answer the number of stops plus one. So if new farthest, let's actually do here. So if new farthest is bigger or equal to target, then we can return target right away here. So we can do num stops plus one. So that's definitely the best choice. And the only issue that we now have is what if we don't have anything, what if it's before the first station? So we also need to check it here, because in this case, for any new station, when we are calculating this new farthest, we might just already be past the target. So we need to check that we are not past the target already. And then if start fuel is bigger or equal than target, then we return 0. Good. So return, we are already returning, and here, if we iterated through all positions and never reach out the target, we should return -1. Okay, so I think I have finished this. Do I start LeetCode before DSA or after DSA? A good thing to ponder. So I think it will be easier and more straightforward to start after DSA, but it's also a good way to learn data structures and algorithms. So if you have some like school curriculum and you have data structures and algorithm as part of it, then you might just wait for it, and then once you pass the course, then you can start doing LeetCode and see how those algorithms can be applied to the actual problems. But if you're just self-learner, then I would suggest to maybe consider using LeetCode as a way to learn data structures and algorithms. However, I myself did learn it, like data structures and algorithms, initially on Coursera before I got a proper education, master's degree in computer science. So you do you, but I don't. Basically, both options might be relevant for you. Okay, now let's go here and let's see if this works on a specific example. But before that, let me check a few things that I have processed my own cases, right? So first of all, let's say that we can reach the target in just the amount of, in just one starting fuel. We are checking this. Now, what if we don't have enough fuel and we also don't have stations, right? So we create the stack for position fuel and stations. We just never go into the stations and we return -1. Okay, so this corner case we also process. What if there is just one station? Think like this, right? So let's actually do that example. Maybe, yeah, no, not this one. This will be too simple to properly test our code, but if there is just one station and it can move us past the target, yes, when we will be reaching the station, we will calculate new farthest and return this numstops +1, and numstops will be 0, so this is correct. Now let's actually calculate for this particular scenario that we are starting with target of, oh, give me a second, 1, 2, 3, 4, 5, 6, 7. The target is 7, and start fuel is 4. And then we have stations, which is at position 0. Okay, we are at position 0. So 1, 2, at 2, 4, and 6. At 2, 4, and 6, we have, I think, 4, 3, and 1. Okay, sounds good. So let's now see how this thing would work. Have I forgotten anything? No, I haven't. So if start fuel is bigger than target, no, 4 is not bigger. So we do here, we create a stack. So stack will be start fuel, which is 4, and number of station, no, 0. So now for position fuel in stations, if we see that, so we are iterating over stations. Let me just have a pointer here. So first we're iterating here. And if we see that stack is bigger, stack, no, that was incorrect. So stack, if stack is smaller than position, no, that was not the right place to check this, right? So we are doing that. Yeah, I think this is, there is a problem with this logic. So let me see. So for example, let's say the starting fuel was 1. So now we are at position 2. So if stack is 1 and it's smaller than the position, oh no, I don't need to check stack 0. I need to check stack, I don't need to check stack the last position. I just need to check the farthest that we can go. So if this farthest that we can go is smaller than this position, then we are returning -1 right here. But now we are starting to check stack from the end. So here, okay, we now have 4. And while stack is smaller than the current position, no, while stack is, so on the stack we will have 4. This position will be 2. So while we have smaller things than our position, we just so smaller, yes, we just need to remove it. But I think there is another issue with this logic. So we are removing, we will never remove anything from the stack here, right? So because stack here, this position is no smaller. This is actually farther, so we can go with 0 steps to this position. And that means that we don't do that. We just do stack pop, and that's correct, right? So here we are, for example, we're popping 5 and 1, but we wanted to choose 7 and 2. Yeah, so let me change this as here to go here, and here we are just popping stack, while we don't get to the position that is actually farther, so we can get to this. And then we figure out how many stations do we actually need, stops do we need to get there. And that's exactly how we get 7 and 1. And we also know that we definitely have something on stack to pop, because we know that at least some element on the stack, the farthest distance that we can go is smaller than the position. So now we are popping this. And now we calculate new farthest, that is farthest distance plus fuel. So okay, we have popped everything from the stack. Now we are also popping this. And then new farthest becomes farthest distance plus fuel. So new farthest becomes... No, actually, it's not farthest distance plus fuel. It's position plus fuel. We are getting the number of stops from there, not the position. Oh yeah, and then what if... But yeah, we are stopping at the station that we popped here. So we need to stop at the station. So that means that this station will always have one stop smaller. So we need to put both things on the stack back. That's good. So new farthest now becomes the position of this station plus fuel of this station. And if new farthest is bigger than the target, so new farthest becomes what? Position is 4, fuel is... Oh, position is 2, and fuel is 4, which is 6. So, and here, we will, just to be clear, we will have 4 and 0. 2 plus 4 equals 6. New farthest is equal... If new farthest is bigger or equal than target, we are returning. It's 6, it's smaller than 7, so we cannot return it here. And we do while stack, and new farthest is bigger than... Okay, while stack is empty, so we are not popping anything. But now we are appending back things. So first of all, we are appending that stack will be new farthest. So yes, and the fuel here, we also need to check if new farthest is bigger than farthest distance. If it's strictly bigger, then we will be updating it. Otherwise, we will not be updating this. Another bug. Wow, that's a tricky problem. Because it might be that we are stopping at some station, and then it will move us in one... We can just move it as one stop, but maybe we can also move like already 10 more stops with just the previous station that we have already stopped on. So we only append things to the stack if they can get us farther than we currently can get at this amount of stops. So we are doing this new farthest number of stops. So if farthest, new farthest is actually 6, so we do append it, so it's 6, and we can get there in one stop, and then we update back, put back this number, right? Cool. We have done one iteration, found like 5 different bugs. Let's go on. So now the station is this one. So we start if this is smaller than the position. No, it's not smaller. 4 is just fine. So we are not returning. And then while stack and stack blah blah blah. So if... No, smaller than the position. Yeah, we only need to remove things that definitely we already can ignore, safely ignore, because they are past us. So it's smaller than the current position. And then we do pop, and it's again 4 and 0. And new farthest will be position plus fuel. So this position plus fuel will be what? 4 plus 3 is 7. And then if new farthest is bigger or equal to target, then actually, yes, it will be returning time stops plus 1, which is 1 stop. So we are returning the correct thing, and we don't ever need to visit the station. I have made so many mistakes here that it might be that I have made more and I just was able to find some of them and not all of them. So yeah, I don't know what's the issue. Let me reload the page. And while I'm doing that, let me check. Okay, no new information here. Oh, I need to log in. Cool, I can do that. Okay. Position is not defined because I just made a mistake in writing this down. Damn. Okay, this is something unexpected. Target start fuel output -1. Yeah, some another corner case that I didn't consider. So we have stations 40 and 50. We can get, oh, we just have a station at 40. Oh, that's stupid. That was stupid. Yeah, I made a big, huge logical mistake that I forgot that we are getting to some station with some actual amount of fuel left. So we don't spend all the fuel to get there. So how this changes our calculations? It doesn't actually change that much, I think. Uh, it just changes the new farthest calculation. Because at this position, we are getting so if we can get to this distance at this number of stops, and we so far have gotten to this position, then it means that this minus position is the amount of fuel that we have left at this point. So it's like, it means that we just need to update this farthest distance plus fuel, and then does it change anything else? Let me think. Yeah, as you can see, I was assuming that we have spent most of our gas. That was a huge issue in my solution. But okay, it solved most of the cases. Yeah, again, the same mistake. Fix it in the source. Okay, let's try again. Wrong answer again. Yeah, and now this is definitely just something that I haven't thought through well. So I'm saying that I can never reach this. But okay, so is it the case that, for example, here, we might get here with less stations, but more fuel, but less stations and less fuel. No, we are only calculating this like this is always under the assumption that we have zero fuel once we get to this station. So if we can get here with smaller amount of stations, this is always dominated. Okay, so where do we return -1 in this scenario? We are going over stations. Okay, I cannot find an error so far. So let me try to debug this. The farthest distance. Okay, so where do we remove? Print position fuel. Print 1. Use test case. Okay, so when we get to this station, okay, so oh yeah, I think this is the issue, right? That we are saying that we can never reach the next station with this number of steps. But we can possibly reach it with more steps, right? So for example, if we start with this 299, and yes, and we do a stop here and do a stop here, eh, or do a stop everywhere, right? Like 21 plus 100, so it will be approximately 300, 400, 421. Yeah, we can definitely reach this station. It's just that we can never reach it in that many stations. So the farthest we can go. So how do we update if we still do stop on this station? we still do stop at this station. What goes happens next? So how do we figure out? We can always stop on some station and add whatever fuel we can get there if we do more stops before. So the problem is that we don't calculate what if we do more stops? How far can we go? So let's say we consider a specific station. So what's missing?
Сейчас котик я буду.
Why we are not storing? Oh, where we can go with? So here, for example, right? Let's see, we're not stopping at this station. Okay, here we are stopping at this station, but what's the farthest that we can go? Let's see when it actually stops working correctly. So after the first station, when we have like 21 fuel, we can get to 320. Okay, so we have updated this. Then 115. That's where we are not updating things, right? So if we have stopped at this station, we kind of need to. So we decide that we are. Yeah, we decided that we are not stopping at this station because. Oh no, we have decided that we are stopping at this station. So we have updated that it's like 115 plus 21. But that's how far can we go in one stop. That's how far can we go in one stop. What if we can go farther in two stops? And we can. Here, right? So here we can do this stop and this stop. And then it will be 21 plus 299. which is 300. And if we could go to 320 with one stop, we can just also increase all the other elements in this list. Yeah, this is becoming an O(n squared algorithm, but we can theoretically just go and append, like add to all the future stops that we are also stopping here. And now the farthest that we can go, and the farthest we can go increases, and the number of stops also increases. So yeah, the problem is that my invariant is incorrect. Because while stopping also on some earlier stops, we can still go even farther if we make more stops. So here we need to also update, like if we make one stop, right? If we make, we need to iteratively update those things. So yeah, I think I figured out this thing, but now we need to do, instead we cannot do monotonic stack because we will be updating elements further down the line. Or can we? Yeah, so what we need to do is now we will need to add iterations over the whole stack. And the stack will need to become double-ended queue. Queue. Okay. So then for element in the stack. And let's actually not store it as lists. So that we can modify things in place. And here we will be doing this. Here we will be doing this. So for while I equals to length of stack -1, while I is bigger than -1, we do that distance stops will be stack I. So now we can also choose to instead stop on the previous stop, right? Stop on the current stop while considering the previous stop. So -1 stop distance will be farthest distance. So that's the one that we can get with -1 stop. So then we can check if we instead need to spend our budget of stops differently. So we just check that if -1 stop distance plus fuel is bigger than distance, then instead of stopping on some other do we guarantee that we can get to this station at all? So okay, I will finish this solution under the assumption that this is correct, but I'm not sure that this is correct. I just want to get done with it. Then I want to spend less time on this. Maybe I should ask for easier hards. But okay, distance and stops will be a stack. If can I always get there? So let's say we consider this position, right? Let's say it's instead 17 and 3, 15, 4. Let's say that we instead consider 17, 4, 19, 5, and we consider 6, fuel, 10, right? So, okay. We can get to these destinations with this amount of stops. Now we do have to stop it at least 2 times to get to 7. So to get to 6, we also need to stop at least 2 times. So now we figured out, okay, if we have 10 of fuel, then in 3 stops we can get to this. But now here, 17, right? Does it mean that yes, so for anything that is still there, we know that we can get here in this amount of stops, right? And we know that we can get here in the smaller amount of stops. So farthest we can go in the number of stops. Can go even further with even more stops, but am I already like n squared solution? Is it worth it even? So maybe I should reframe it as a dynamic programming problem. Like how far can you go in case stops. So let's say that we have just one stop that we can make. And then it will be like we spend the first amount of fuel, and then we get to like whichever stations that we have, and then we make possible stops there, and we get maximum possible destination. But then what if we can make 2 stops? Then we can choose any 2 stops up to this point. So then it becomes a question of which 2 stops to choose. Depending on the position, it will always be the same 2 stops that we will be choosing, because for any position there is an optimal sequence of stops to make to get to this position. Then what if, then again for the 3 stops, for the 4 stops. So is it just that I need to also to append? No. Yeah, basically I feel like this is not the right solution. So stack if stack, then farthest max distance and stops equals this. Yeah, maybe this is enough. And then I just need to do stack append left. So if we can get to max distance in this amount of stops, then we can just make the stop right now and get to max distance plus fuel and stops plus 1. So let me go and change this all back. So I think the problem might be that we just don't try to update. Don't try to update that we can actually make this stop here, and now we just need to like whatever is the maximum distance, we make one more stop and we can get there. So then we just don't never consider making this stop, and then we have a relatively empty stack compared to what we could have if we stopped everywhere. So we always try to stop. Oh yeah. Still incorrect. Yeah. The same scenario is incorrect because that's not enough. We also need to update. We are just updating the last one, but it looks like we need to update through the whole stack, so it makes it all n squared. And I'm too tired to finish this. Oh, damn. 1 hour 23 minutes and I still haven't solved it. But thanks everyone.